Welcome to this video. In this video we will do some examples of how to apply Ohm's law to find voltages and currents in simple circuits. An additional benefit of this video is that we will start using some of the metric prefixes for that modify the amount of current or voltage. So we'll start, or resistance. So we'll start using k ohms for kilo ohms. We'll start using milliamps. We'll start using maybe even microvolts or microamps. We'll see how it goes. But again, the primary purpose of this video is to do a couple of examples with simple circuits to show you how Ohm's law is applied. So let's start with a simple circuit. Let's suppose we have a voltage source of 3 volts and it's connected to a resistor that has resistance of 1 ohm is not the best choice here, so we'll do 2 ohms. So we'll start off with a very simple circuit. Okay, so the way we solve this is to recognize that everything that's connected to this wire is a single node and there's no voltage drops from any point on the wire to any other point on the wire. Everything that's connected to this node is also a single node, and so there's no voltage drops anywhere on this wire, which means that the voltage between any 2 points that are connected to my green node on the top and my red node on the bottom have the same voltage across them. And my voltage source will do whatever it has to do to make sure that the voltage between these 2 nodes is 3 volts. So the voltage across this resistor is 3 volts. Now let's suppose that our goal is to compute the current going through this resistor. Well, we know from Ohm's law that the current is equal to the voltage divided by the resistance. In this case, the voltage is 3 volts and the resistance is 2 ohms, which means that the current is 1.5 amps. So there you have it. That was pretty easy, wasn't it? Let's modify this a little bit to see if we can make it a little more interesting. And to do that, I'm going to change the problem just a little bit. And this will start to bring in these prefixes. So instead of having a resistance of 2 ohms, let's suppose I have a resistance of 2 k ohms. Okay, K is the metric prefix for 1,000, so this represents a resistance of 2,000 ohms. Okay, depending on what sorts of circuits you're working with, if you're working with electrical circuits, op amps and signals and stuff like that, you're much more likely to see resistances in the order of k ohms or even megohms. If you're working with electrical power, you might be seeing resistances on the order of 0.1 ohm or something like that. And so for the same voltage, what you get in power applications is a much larger current than you'd get in a typical circuit application. But I digress. So suppose that we have now 2 k ohms and we want to find the current. Well, it's still V over R. The voltage is still 3 volts. But now the resistance is 2 k ohms, which is 2,000 ohms. After a while, you may not need to write it out this way, but if you're beginning, this is probably a good idea. And this then turns out to be if I work it out, 0.0015 amps. So I could leave it like this. This is a perfectly valid solution, but it turns out it's not the way most people are used to doing it. You can see that this 0.0015 amps is the same as 1.5 times 10 to the minus 3 amps. This is just scientific notation, right? And if I have 10 to the minus third, the appropriate prefix from the metric system is a small m, which stands for milli. So this is equal to 1.5 milliamps. So typically, when you work these problems, you'll see the resistance given in terms of k ohms, and if your voltage is on the order of 1 to 10 volts, something like that, your answer will probably be a current that is in milliamps. Okay, so that's example number 1. We have a voltage source connected to a resistor. Let's see what happens when we have a current source connected to a resistor. So now let's suppose that we have a current source, and we'll give it, say, a value of 2 amps. And suppose it's connected to a resistor that has a value of 7 ohms. Okay, and our goal now would be to find the voltage across this resistor. Okay, well, the way we would approach this, it turns out that we know what the current is that's going through this resistor. The current going through this resistor is 2 amps. How do we know that? Well, this current source will do whatever it has to make sure that 2 amps goes out of it, and then 2 amps comes back in. So if 2 amps are leaving the current source, the only path that it has to follow is through the resistor and back around to the current source. So basically, we know that the current through this resistor is 2 amps. Now we can apply Ohm's law, and the voltage will be 2 amps times 7 ohms. Again, this is I and this is R, which when we work it out is 14 volts. So that basically says that across this resistor will be 14 volts. And what that means, in order for the current to be 2 amps through the resistor, what that means is that this current source is also going to have 14 volts across it. And again, the current source is going to do whatever it has to make the current through that resistor be 2 amps. In this case, it has to have a voltage across itself of 14 volts. Okay, so that was a fun example. Let's suppose that we want to change things up a bit. So we'll change the values of our current and resistance. So let's suppose that instead of a current of 2 amps, we'd like to have a current of 2 milliamps. And instead of a resistance of 7 ohms, we'll have a resistance of 7 k ohms. Okay? So again, 2 milliamps is 2 times 10 to the minus 3 amps. 7 k ohms is 7 times 10 to the 3 ohms. We might also write this as 0.002 amps and 7,000 ohms. Okay, well, the voltage across this resistor is going to be I times R. I is 2 times 10 to the minus 3 amps. R, oops, I don't actually want to write R. That's not very bright. R is 7 times 10 to the third ohms. And if I work this out, the 10 to the minus 3 times the 10 to the third turns out to be 1. So I end up with a total, or a 14 volt result. Okay, so again, what this means is in this case, the voltage source will do whatever it has to make the current through the resistor be 2 milliamps, and given that I have a 7 k ohm resistor, that requires a voltage of 14 volts. Okay, so let's do one more example with this circuit. Tidy up after ourselves first. And for fun, let's suppose now that we want the current, well actually, we need to probably get rid of this voltage here too, because there's no guarantee that when we change values we'll still have 14 volts. In fact, I'll be sure to pick values where we don't have 14 volts. So let's suppose now that the current is 2 microamps, which, if you remember your prefixes, this is 2 times 10 to the 6th amps. That should be 10 to the minus 6th amps. And I won't write it out as an equivalent decimal because I feel sort of lazy. And let's suppose that we have a resistance of 10 k ohms, which again is 10 times 10 to the 3rd ohms, and I guess I could write this out as 10,000 ohms, although I probably won't do that much anymore. Well, the voltage now across that resistor is going to be the current times the resistance, and when I work this out, I get 20 times 10 to the minus 3rd volts. Okay, 10 to the minus 3rd again is we replace that by a prefix of milli, so we would have here 20 millivolts. By the way, these values are actually fairly typical of values you might see if you're working with a sensor system and you're trying to get data off of something that acts like a sensor that acts like a current source. So anyway, that concludes our video on Ohm's Law examples. You should at this point now be able to work these simple examples or these simple circuits where you have either a current or a voltage source connected to a resistor, and hopefully you begin to see how we use the prefixes to make our notation much simpler at the expense potentially of making our computation a little worse, but when you get used to it, it's actually not bad at all. So that concludes this video.